Today we're going to talk about heating and cooling curves. Heating and cooling curves are a measurement of, well, to make a heating or cooling curve, you take a substance and you continually heat or cool it. So you either add or remove heat at a constant rate. While you are adding or removing that heat, you're continually measuring temperature. Now, what you would think is as you continually add heat to something, its temperature just goes up. But as you can see, if you're looking at this heating curve on the page, there are some regions in the graph where that actually doesn't happen. And we're going to actually see that in the lab, which will be really nice. So the very first region on our heating and cooling curve, region number 1 right here, is the solid state. And this is where only solid matter is present. So if you imagine that this substance that we're heating at a constant rate is water, anywhere during unit 1 on this graph, we would just have solid ice. So that's what's going on in this very first little unit right here, which as you see is below 0 degrees, so it makes sense that that would be ice if we were talking about water. Region number 2 is one of these flat regions that we see. So at 0 degrees Celsius, if you're continually adding heat, what's actually going to happen is melting. Our science word for this is fusion. So what's actually occurring here is our solid water is turning into liquid water, and there are both solid and liquids present in this state. We see this a lot around here in the winter when we have those days that are right at the freezing point, and you kind of get that slushiness. So there's like some frozen, some liquid, kind of all mixed together. Region number 3, if we're continually heating here, which is going from 0 to 100 degrees Celsius, is representing our liquid state. You do notice that the temperatures are increasing as we are continuing to add heat, and this eventually will take us up to 100 degrees Celsius. At 100 degrees Celsius, for a sample of water, we expect boiling or vaporization to occur. We could also have the passive version of this, which is evaporation, occur as well. During this phase, both liquid and gas are present. You may have noticed before, if you're kind of boiling water and you get that steam, kind of the wet feeling that steam really does have to it. And finally, section 5 on the graph is showing above 100 degrees Celsius for a sample of water. This would just be the gas state. And so what we kind of call steam, or we would just have, or water vapor even. We continually can raise the temperature at this point. The only phase of matter we have present is a gas. So what's kind of interesting about a heating or cooling curve is it shows the progression through the temperatures as we are adding heat. In this case, is the heating curve, or adding heat. And you can see where phase changes occur by these flat areas in the graph. So these areas in the graph that are flat are actually showing where you have a phase change occurring. Now, what you also have to be able to do is talk about kinetic and potential energy changes during each region of the graph. So kinetic energy is the energy of motion. Temperature directly measures kinetic energy. Potential energy is the energy of position. An individual temperature can't really tell us always if potential energy is changing, but we can determine this if we have several different temperatures. So there's no way to really easily directly measure potential energy. We kind of have to do that by measuring temperature a few times. So I'll talk about that in just a moment. Now I'm going to go back to our graph. We need to be able to talk about kinetic and potential energy in each region of the graph. Region 1, right here, we have an increase in temperature. Temperature increasing tells me kinetic energy is increasing. We can probably make the assumption that potential energy is staying pretty much the same here. Region number 2, where my kinetic energy, or my temperature is constant, that means my kinetic energy is also constant. However, I'm still adding heat, so what is changing? Potential energy is changing. As that heat is being added, potential energy is increasing. Region 3, again, is showing kinetic energy increasing. increasing here. So our temperature is going up, our kinetic energy is going up. Region number 4, kinetic energy will again remain constant. Potential energy is now increasing again. So potential energy changes during phase changes, you will notice. And again, we get back to region 5, and our kinetic energy is increasing again. So some form of energy is changing if we're putting energy in at a constant rate. If temperature is remaining the same, that's telling us that potential energy is what is changing. So again, just to kind of, go over this one more time. Section 1 was where we had our kinetic energy increasing. Section 2, kinetic energy constant. Potential energy increasing. Section 3, kinetic energy increasing. Section 4, kinetic energy constant. Potential energy increasing. And section 5, our kinetic energy is increasing. So a cooling curve is what we would have if we removed heat. So we're probably going to start at a pretty high temperature. So I'm going to start up top. As I remove heat, my temperature will decrease. So if I imagine up here that I am at the gaseous state, I will cool this down until I hit a temperature right here known as the boiling point. The boiling point is that transition between a gas and a liquid. If I continue to cool this down, it'll go into the regular old liquid state until it gets to what we call the freezing point, which is where I will have a transition between liquid and solid, and then finally I will end up down in my solid state. You have to also be able to describe potential and kinetic energy changes in this graph. The difference here is because we are removing heat, which sometimes we measure this, it says time down here because sometimes we measure this as a function of time. We just constantly remove heat over time. So wherever my temperatures are changing, they're now going down. So kinetic energy is going down here. Potential energy is going down. Kinetic energy is still going to be constant. During my liquid-only phase right here, my kinetic energy is again decreasing. Here I've got my potential energy decreasing. My kinetic energy is going to stay the same. And then finally, as I continue to remove heat from the solid state, my kinetic energy will decrease. So whether or not you're looking at a heating or cooling curve, it's kind of the difference between looking at things in two different directions. So as we're heating, we're going up, we're adding energy, and all of our types of energy should always be either going up or sometimes remaining constant. We're looking at this from the cooling standpoint, energy is going down unless it's remaining constant. So I got a lot of definitions to throw at you. Fusion is another word for melting, and that's a change of a solid to a liquid. Freezing, when a liquid changes to a solid. Pretty standard term. Vaporization is a transition between liquid and gas. Evaporation is a version of vaporization that is considered to be passive because you're not specifically adding heat. So if you boil something, you turn on the burner, you really actually specifically put heat into it. With evaporation, you're not doing that. Evaporation is just energy from the surroundings ending up going into a sample, and eventually some of those molecules become a gas. Condensation is when we have a gas change back into a liquid. And then a special example is sublimation. Sublimation, this is a solid changing directly to a gas. Sublimation you see in the case of dry ice. So dry ice, actually, if you've ever had any experience with it, is carbon dioxide that starts as solid. It's very cold, but instead of melting to a liquid state, it actually turns directly into a gas. So deposition is actually the reverse of this process. It's when a gas changes straight to a solid. and we don't actually see this quite as much. So that's the important terminology that you need to know in order to talk about energy changes and phase changes on a heating and cooling curve.